Hi there. Welcome to this presentation on our article about the fusion algorithm for the hidden shift problem in finite abelian groups, which my colleague Carlo and I will present. The other authors of the paper are Wouter Kastrijk and Anne Dooms. We will first explain what the hidden shift problem is and why it is important in cryptography. Then we will explain some previous quantum algorithms for it. And finally, we will explain our algorithm.
So the hidden shift problem is stated as follows. We are given an abelian group G with the addition as operation, together with a set X and two injective functions F1 and F2 from the group G to the set X. And there's some unknown element S in the group, such that this equation here is satisfied. In other words, the functions F1 and F2 are shifted versions of each other. And the goal of this problem is to find this element S using evaluations of the functions F1 and F2. This hidden shift problem appears in several cryptographical settings, for example, in crypto systems based on lattice theory or in crypto systems based on hard homogeneous spaces, which will be explained later on in this presentation. And it's important to note that up to now, there is still no known quantum algorithm which can solve the general abelian hidden shift problem within polynomial time. So let's first give an example. Let's take the group G to be the direct product of m copies of the group Z modulo 2. And in this concrete setting, the hidden shift problem is called Simon's problem. So basically, the elements X and S are then vectors in an m-dimensional vector space over the field with two elements. And for this specific problem, there is, in fact, a polynomial time solution to solve it. And this method relies on the so-called standard method, which will also be explained later on in this presentation, to generate quantum states depending on a character of the group. So what is a character? A character is a group homomorphism from the group G to the set of non-zero complex numbers with a multiplication. This is also a group. So basically, we associate every group element to a non-zero complex number such that addition in the group corresponds to multiplying the associated non-zero complex numbers. In this specific case, we have 2 to the m characters indexed by a vector v applied to a vector w, which are actually powers of -1. And the exponent is the inner product between the vector v and w. So note that this character can only take the values 1 and -1 in this group. So if we have this state, the superposition of 0 and 1, we can apply the Hadamard transform. So we obtain this state. We measure either the value 0 or the value 1. If we measure 0, we know that our character chi v of s cannot have the value -1, so it must have the value 1, which means that the inner product of the vectors v and s must be 0 modulo 2. And on the other hand, if we measure the value 1, we know that chi v of s cannot be 1, so it must be -1, which implies that the inner product between v and s must be 1 modulo 2. If we gather enough such linear equations, well, actually polynomially many, we can just use simple linear algebra to reconstruct the value s and hence solve the hidden shift problem for this specific group. And this idea will reappear later on in this presentation.
The hidden shift problem is important in cryptography because it is connected to the quantum security of key exchange protocols. There is an abstract generalization of Diffie-Hellman key exchange that is based on group action of a commutative group G on a set X. The idea is as follows. There's a public element X of the set, and then Alice and Bob each choose a random element of the group G. They apply it to X and send the result to each other. Then they each apply their secret group element to the thing they received from each other, and they find the same secret key. So what actually is a group action? Basically, you plug in a group element and an element of the set, and an element of the set comes out. There are two conditions that need to be satisfied. Applying the neutral element of the group to X gives back X, and applying S1 plus S2 is the same as first applying S2 and then S1. Though the order of applying group elements doesn't actually matter for commutative groups. So now I can define two problems. The vectorization problem asks, given X and S star X, find S. And the parallelization problem asks, given X and S1 star X and S2 star X, find S1 plus S2 star X. The Diffie-Hellman protocol we saw in the previous slide depends on the hardness of the parallelization problem. And obviously, if you can solve the vectorization problem, you can also solve the parallelization problem. It turns out that with a quantum computer, the opposite also holds, and the two problems are equivalent. Now, if you can solve the hidden shift problem, you can solve the vectorization problem. The element S star X can be used to construct a map sending A to A star S star X, and the element X can be used to construct a map sending A to A star X. And it turns out that the map F1 is just a map F2 shifted by S. So we have an instance of the hidden shift problem. Seaside is an example of a key exchange protocol based on a group action. The group is the class group of an imaginary quadratic ring O, and the set acted upon is the set of supersingular elliptic curves over the prime field Fp, whose endomorphism ring is isomorphic to the imaginary quadratic ring O. The action is via isogenies of elliptic curves, so the quantum security of Seaside depends on the hardness of the Abelian hidden shift problem.
We have already mentioned this standard method. So what is it exactly? We start from the uniform superposition over all the elements in the group, and we apply the functions f1 and f2 in another register. We measure this register to obtain some value f1 of g, and the state collapses into a superposition of the states g and g plus s. Afterwards, we apply the Abelian quantum Fourier transform on this state, and we measure a character of the group randomly. So then our state collapses into a superposition of 0 and chi of S1. So this is the way to construct the states depending on a character chi of the group G. Our contribution to the solution of this hidden shift problem is a continuation of ideas by Kuperberg, Peikert, Friedel, and also Childs, Zhao, and Sukarev. All their ideas are based on the fact that we can use this standard method to generate these kinds of states depending on a character of the group. It all started with Kuperberg, who had the idea focusing mostly on cyclic groups of order a power of 2, which means that the characters of the group are actually taking powers of a 2 to the nth root of unity in the complex numbers. His idea was, if I can somehow generate a character where the exponent is a high power of 2, as high as possible, but not 0, we can just apply the Hadamard transform we have seen before in Simon's method to retrieve the least significant bit of our hidden shift S. And then we can reduce the problem to a group which is smaller by a factor of 2. So we can recursively reconstruct S bit by bit. But how can we generate this character? Say that we have two characters where both exponents are odd. By taking the tensor product of two such quantum states, we actually multiply the characters together, but we get either the sum or the difference of the exponents. But the sum or difference of odd numbers becomes even, and the sum or difference of exponents divisible by 2 becomes divisible by 4, etc. So that's how we can generate higher powers of 2. And this idea will become important later on this presentation. This algorithm, though, is sub-exponential in time and sub-exponential in memory, but Oded Regev improved this algorithm by making a memory-friendly version of it. His idea was to combine more than 2 of these quantum states to create longer vectors, and also store some information about the character in another register, such that upon measurement, actually the characters are forced to lie in some more structured set. So this algorithm becomes memory friendly, but again, the focus lied mainly on cyclic groups of order power of 2. And then Childs, Zhao, and Sukharev generalized this to abelian groups in general. Kuperberg, in a second paper, then formalized this idea and called it a collimation sieve. And he first used the term QRECM. And QRECM stands for Quantum Random Access Classical Memory, which is a cheaper version of regular quantum memory. But he also mainly focused on the case where the group is cyclic of order a power of 2. But in both his articles, he briefly mentioned the generalization to cyclic and also abelian groups. But then Peikert gave a different view on this algorithm by explaining that it's not necessary to reconstruct S least significant first, which actually concerns divisibility by 2. But instead, he gave the example of reconstructing the hidden shift S most significant bit first, so that you only have to use the order of the integers, and it's easier to analyze this algorithm for cyclic groups. So our contribution, our algorithm to solve this problem consists of 3 parts, namely the torsion part, a collimation part, and a combination of the 2. So let's start with the torsion part. We will assume that we're working in a finite abelian group, where if we take the pt to the tth multiple of any element in the group, we get 0. But p and t, well, p should be a small prime number and t a small non-negative integer. So let's, for the sake of illustration, just take this group over here with a 3 torsion part and a 4 torsion part. The idea will be to first focus on the 3 torsion part, so reconstruct the hidden shift in that component, and then reduce the problem to the 4 torsion part. So recall that we can associate every character of the group to an element in the group by this definition. The idea will be to combine characters like Kuperberg did in a similar way, but not exactly the same. But we want a character of which the third power becomes trivial. So this is done by combining these vectors in a way such that a3 becomes divisible by 4 and a4 becomes divisible by 2. Once we have done that, for example, if we have this character associated to the vector 1, 2, 0, 0, of which the third power is trivial, we have this quantum state. We apply the Hadamard transform to it to get this. If we measure 1, we know that chi of S cannot be equal to the complex number 1, which means that this integer linear combination is not 0 modulo 3. So if we apply Fermat's little theorem, we get that the square of this number is equivalent to 1 modulo 3. And expanding this using the binomial theorem, we get a linear equation in the monomials in S1 and S2. And after gathering enough such equations, we can reconstruct S1 and S2 up to a scalar multiple, but there are several workarounds for this problem. For example, introducing another factor in the group where we know that the component of the hidden shift must be equal to 1. So once we have reconstructed the part of S in the 3 torsion parts, we can focus on the 4 torsion parts. Then our idea will be to generate a character of which the square is trivial. So our character can only have the values 1 or -1. And we have already seen this in Simon's problem. So if we have a character of which the square is trivial, we apply Hadamard transform, measure 0 or 1, we get a system of linear equations, and by linear algebra, in the same way we have done in Simon's problem, we can reconstruct S3 and S4, hence reconstruct S in this P2 to the T torsion group.
I am now going to explain to you very roughly how our collimation algorithm works. The ideas we will present here are due to Cooperberg and Peikert and others, and we make them more concrete, and we give one particular way of doing collimation on arbitrary abelian groups. So collimation is based on long phase vectors. We call that the standard method produces qubits that can be regarded as length 2 phase vectors. These length 2 phase vectors can be combined to longer phase vectors. A phase vector is an expression of the form you can see here. And the hidden shift S is encoded via characters chi. We call the set of all characters G dual. So the idea is to combine bad quality phase vectors into good quality phase vectors. In the beginning, you have phase vectors where the characters are randomly spread out across G dual. During the collimation process, you get phase vectors where the characters are concentrated into smaller and smaller regions of G dual. At the end of the process, the phase vectors have their characters packed together into a region so small that every character in this region occurs at least once in the phase vector. One then has to thin out the phase vector and relabel the terms so as to obtain a highly regular phase vector supported on some subgroup H of G dual. And then one takes the Fourier transform to learn the hidden shift model of the kernel of H. If H is very large, then we have to do one extra step. We tensor multiple highly regular phase vectors together to obtain one that is large enough to fill the whole subgroup H, and then do a Fourier transform. Once we know the hidden shift model of the kernel of H, we can reduce to the hidden shift problem in the kernel of H. We will now give an example to illustrate our version of collimation. Everything is based on taking a chain of subgroups of G dual where each quotient of successive subgroups is cyclic. Now there's two ideas. You want to get the characters of our phase vectors into smaller and smaller subgroups that occur in our chain. And for a given cyclic quotient, you want to get the characters into smaller and smaller intervals of the cyclic quotient. So we start with the phase vectors at the top, which are the bad quality phase vectors, where the characters are randomly spread out over G dual. And each collimation step takes two phase vectors and gives one phase vector of better quality until you end up at the bottom of this tree. In this example, G3 over G2 is large. So we write the cyclic quotient as all numbers from 0 to some number, and we regard this as an interval. Each character has an image in this interval. In the first collimation step, we force all the characters into smaller intervals. And in the second step, we get all the characters to map to the identity element of this quotient so that all characters belong to G2. And finally, we apply the last collimation step where all characters end up in the group G1, which is small enough that all characters of G1 occur at least once in a phase vector. And now it is time to combine our torsion algorithm and our collimation algorithm. This will only be useful if you have a large abelian group with a large subgroup of low exponent. For instance, if there are lots and lots of elements of order 20. The idea is to first do collimation using a chain of subgroups where G1 is P to the D torsion subgroup. So we do collimation to make length 2 phase vectors with characters in G1. So this is a machine that produces phase vectors that can be used as input for our torsion algorithm. This torsion algorithm then gives us the hidden shift modulo P to the D G. And this reduces the situation to the hidden shift problem in P to the D G. One then applies our collimation algorithm to this subgroup of G. So we have collimated twice, and the depth of our collimation tree will be less than if one cannot exploit a large low exponent torsion subgroup.
To summarize, we have combined ideas of Friedel, Shayi, Peikert, Cooperberg, and others to create an algorithm to solve the hidden shift problem. It works for any abelian group G with this complexity, and the notation P2 to the Tg means the subgroup of G without the P2 to the T torsion elements. This algorithm affects the security of crypto systems based on hard homogeneous spaces, but we do like to stress that our algorithm is only better for groups which have a lot of P2 to the T torsion elements, where P is a small prime number and T is a small non-negative integer. So for example, if the group is isomorphic to Z2 times Z3 times Z5 times Z7 times Z11, there are better ways to solve the hidden shift problem. So this raises some questions for possible further research. First of all, can a more detailed analysis or different methods improve our knowledge about the complexity, or maybe even improve, so reduce the running time? And there are algorithms which replace P2 to the T torsion by M torsion, where M is a general natural number. Is there some way to incorporate this into our algorithm while still keeping it memory friendly? Thank you for watching this presentation. I hope you enjoyed it.